when we're looking at early ideas in chemistry, uh, Lysippus was the first person to actually propose that matter was composed of what he called small, indestructible particles. Um, Plato and Aristotle did not really like this idea, so back in the day, this wasn't really held into any regard. But I think it's an interesting story that the book kind of dives in through. Today, we have the scientific method, right? And we've hopefully all seen the scientific method in some way, shape, or form. Its two main ideas are observation and experimentation. When we decide to think about the scientific method, a good thing to think about are these two overarching ideas. Observation. What do we see in nature? Can we create a hypothesis? A hypothesis doesn't hold much weight. It's just my opinion. It's a statement of my observations. It has no backing, no experimentation, just my observation. With that, then we can experiment. And so with the experimentation, now we can start to develop an idea of data. We get data to back our observations, and we get to see what does that actually look like. Now, there are a couple of different types of data. We're not going to spend too much time on the scientific method. We want to get to the specific experiments that we see in our history. But scientific data can either be qualifiable or quantifiable. Qualifiable meaning describing how something happens, color, shape, smell, those are all qualifiable. Qualitative is the same idea there. Quantifiable is what we think of mostly when it comes to chemistry. Not that qualifiable is not valid. They're both very important for us, but quantifiable data is things that we get in the lab most of the time. Quantitative meaning we're measuring or quantifying something about the process itself. Subjective for qualifiable, meaning my opinion, right, is most often put into qualifiable things. If I think something's hot, you might say it's very hot. If I say it's really cold, you might say, well, it's not that cold, it's cool. So very subjective based off of the scientist. Quantifiable is objective. I get a number. It's 72 degrees outside, right? So we can see how temperature can be both qualifiable and quantifiable. Now, the early ideas, who came up with a lot of these things. One of the big name players that we'll see a lot repeated over the course of the semester is John Dalton. He was the first to offer convincing evidence to the discussion of matter is created by small particles idea. All right, for the law of conservation of mass, this law states that matter cannot be created nor destroyed. Matter can be transferred, though. What this means is that I can't go into the lab and expect to create matter out of thin air, right? I take some reactants, I can transfer them to different molecules that are my products. But in order to satisfy the law of conservation of mass, I have what we call a balanced equation. Now, Antoine Lavoisier, who is one of my absolute favorite chemists, I'll tell you why in just a second. Antoine Lavoisier was a French chemist. He lived from about 1743 to 1794. You do not need to know those dates. Those dates are just for you to appreciate. We're painting a picture right now of where we came from. So Antoine Lavoisier was a French chemist, and he studied combustion. The guy, why I love him, is he studied reactions that blow up. Like, how cool is that? Combustion reactions, in general, you take some sort of a fuel, which is usually a hydrocarbon. Hydrocarbons, meaning it has hydrogen and carbon in it. You react it with oxygen gas. I'm going to put a little G there. That tells you the state of the matter, right? And you create carbon dioxide gas and water vapor, H2O gas. All of those being the state, helping identify the classification of matter. Now, with combustion, Antoine Lavoisier did a couple of very important experiments. And namely, what he did was he studied combustion with careful measurements of the mass of all of the objects over here. These are called the reactants. Sometimes those are called the starting materials. They're the things on the left. It's what we start with. And he measured those very precisely, right? He can have their mass, and then he reacted them to form the products, what we end up with. And when Lavoisier measured the reactants and compared it to the measurement of mass of the products, what he noticed was that they were the exact same. And so he went through the scientific method in order to say, my observation was that mass is consistent in a reaction. He hypothesized that the fuel mixes with oxygen to form the products. And then he developed his experiment. And that experiment generated this data. And the data said the mass of the reactants is always going to be equal to the mass of the products. Super amazing to start seeing this development of our scientific method with Lavoisier and his study of combustion. A hypothesis, again, is just a tentative interpretation of an observation. He didn't quite get to the law yet. It's not until you actually get to data. So let's scroll down here and say, lots of data. Then you can start to generate a law. Now, what is a law? A scientific law is readily tested. It is not something that is truth. I don't want us to think truth. Scientific law is a brief statement, we'll say, that summarizes past observations and predicts future ones. So the law of conservation of mass says this. We'll scroll back up there. Matter cannot be created nor destroyed, but it can be transferred. We can see that every single time we do a reaction. In the past, Lavoisier measured the mass of the reactants. He did the reaction and he measured the mass of the products. And the data shows that the mass is the same for the reactants as was the products. So no matter was lost and no matter was gained. It's always consistent. I predict, based off of this law, that any other reaction that I do from here on out will be conserving mass. The mass of the reactants should be equal to the mass of the products. Now, a theory is something quite different. A theory is something that takes all of the law and all of the data with the law, and it creates a model, that model for the way that nature is. And it tries to explain that. It can be a collection of laws, but the main thing that we want to think about with this collection of laws is the idea that a theory explains how nature behaves. Notice in the law of conservation of mass, it just says this is what's going to happen. It doesn't tell you how. It doesn't tell you why. It just says this is what's going to happen. A theory takes all of our observations, it takes all of our predictions, and it helps explain why we see what we see. So we'll dive into a couple of more laws, and then we'll get into Dalton's atomic theory. All right, the law of definite proportions was developed by a man named Joseph Proust. He was also a French guy in the late 1700s. Lots of things happening in this time period. He summarized the law of definite proportions this way. All samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. What does that mean? H2O is H2O, no matter where you get it. What we call water will always be one oxygen, and two hydrogens. That little 2 subscript goes to the number of hydrogens. When we think about the law of definite proportions, it's literally saying when I have a name for something like water, that water is established with a specific ratio of elements. And this is how Joseph Proust was able to do it. The decomposition of 18 grams of water always resulted in a 16 gram to 2 gram ratio of hydrogen to oxygen. Now, when we think about that reaction, hydrogen and oxygen, we'll discuss later why there's those subscripts too. They form diatomic gases in nature, and we'll talk about that a little later. We'll also learn about balancing equations in just a little bit. But what the law, this example of for the law of definite proportions tells us is that if I had 16 grams of oxygen to 2 grams of hydrogen, that ratio of 8 grams of oxygen to 1 gram of hydrogen, I just reduced it there, will be consistent no matter the sample, right? So let's just pretend that I had 36 grams of water. It will decompose every single time to 32 grams of oxygen and 4 grams of hydrogen. And the reason for that is because of the ratio, still an 8 to 1. Now, here's a type of example of a question that you could see on an exam. 2 samples of carbon dioxide decompose into its constituent elements. One sample produces 25.6 grams of oxygen. The other produces of oxygen and 9.6 grams of carbon. The other produces 21.6 grams of oxygen and 8.1 grams of carbon. Show that these results are consistent with the law of definite proportions. Are they the same molecule originally? Well, let's take and do the ratio. Oxygen to carbon, or you could do carbon to oxygen. It doesn't matter which one you put on top. But this way tells us that there is a 2.67 to 1 ratio of oxygen to carbon. Wonderful. Doesn't need to be a whole number yet. These are just masses. Let's do it again. 21.6 grams with the other sample, 8.10 grams of carbon. And what we can see in that ratio is the same exact 2.67 of oxygen over 1 carbon. We won't spend too much time on the law of multiple proportions, but what it clearly just states is that if a molecule / sample has a different mass ratio of constituent elements, it's a different compound. H2O versus H2O2. Both consisting of hydrogen and oxygen, but in a different ratio. And that's what we have to say is water versus hydrogen peroxide are different. They'll have different properties. They'll have different reactivities. And that's what the law of multiple proportions just says. We'll see that in a couple of other ways too. Carbon with one carbon versus carbon, with two carbons, right? Carbon and hydrogen can go and create a bunch of different things. The law of multiple proportions, it simply just states just because you are created with hydrogen and oxygen, you don't necessarily have to be water. You could be a bunch of other different things too with different mass ratios. Now, John Dalton took all of this and developed his atomic theory. And what John Dalton's atomic theory explains are these four postulates. Postulates are just statements of what the theory talks about. The first one says that each element is composed of tiny, indestructible particles called atoms. The second one, all atoms of a given element have the same mass and other properties that distinguish them from other elements and atoms of other elements. So this looks at, the law of definite proportions. A little bit also in terms of the law of multiple proportions. We'll get into some of the issues with these in just a second, but 3 says atoms combine in simple whole number ratios to form compounds. Wonderful, that's again the law of definite proportions. And atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms change only the way that they are bound together with other atoms. This is the law of conservation of mass. Now he took these and he broadened the laws and he changed the definitions to fit his theory. A couple of issues with these that we see now. Number 2, not all atoms of a given element have the same mass and other properties. We're going to dive into next time isotopes. Isotopes are an issue. We'll define those in the next lecture. And number 4, a little issue here. Nuclear reactions we know now exist. Now, the discovery of the electron was J.J. Thomson, late 1800s. So we've moved quite a far distance away from our idea of when we looked at what we were just looking at with the laws and the development of the laws. J.J. Thomson was the first to observe that a beam of particles called a cathode ray traveled from a negatively charged electrode, called a cathode, to the positively charged end, called the anode. That's very important to be able to say negative versus positive, right? That flow told us that he was discovering the electron. We'll get in there in just a second when we see a picture. The particles that composed the cathode ray had the following properties. They traveled in a straight line. They were independent of the composition of the material from which they were originated, the cathode, and they carried a negative electric charge. How did he know that? Because they originated at the cathode and they traveled towards the anode. So that negative little charge, that's my abbreviation for the electron, E with a little negative charge up there, was one of the observations that he had. Now, what you would really want to get out from these discoveries, these are all observations, right? They're all observations. You can get an experiment to then collect data. J.J. Thomson was able to measure the charge to mass ratio of the cathode ray by deflecting them using electric and magnetic fields. He was able to get this value, negative charge being the electron, negative 1.76 times 10 to the 8 coulombs, which is an electrical charge per gram. So this is a charge to mass ratio. Notice charge in coulombs per gram divided by grams. Now, that data was developed by this type of an experiment. This is a normal cathode ray up here. It's connected to a high voltage battery inside this beautiful glass tube, hand blown at the time, right? When we think about what's inside of there, it's partially evacuated so that there's no air resistance. And the electrons always traveled from the cathode to the anode. What J.J. Thomson did was he made this bottom alternate cathode ray type of experiment. Here's the general start, right? Here's that general anode and cathode that we saw up there. And what he did was he put a little hole through the anode so that the electrons could pass right through. And so undeflected, they went right back through to a detector, probably photo paper. But what he was able to do was take these electrically charged plates and a magnet and start to bend the actual beam in the backside of this evacuated tube. He kind of made it like a balloon shape so that he could deflect. And the deflected beams, he was able to actually measure the amount of deflection, the mass of then the charge to mass ratio. Notice for his experiment, that charge to mass ratio, he was not able to find the actual charge or the mass itself, just the ratio. And that was it. Now, what he was able to take for us was the idea that the electron was negatively charged. And it was a low mass particle. The charge, negative 1.67 times 10 to the 8 coulombs per gram. That idea tells us the numerator is very, very big. The denominator is very, very small. So the electron mass itself was small, smaller than any other atom that he had that was discovered at the time. And so that idea of being negatively charged, he started to identify the properties of electric charges. Opposites attract. A positive and a negative come together, right? Like charges repel. So two positives putting together would repel each other. The arrows go opposite. Say opposites attract. Two electrons, two negatively charged things, repel each other. From the J.J. Thomson experiment, Millikan came by. Now, Robert Millikan was at the University of Chicago. In 1909 was when he did his experiment. Late 1800s for J.J. Thomson. He was working out of Cambridge. And so probably about 10 to 15 years after the original cathode ray experiment, Millikan decided to do a drop oil experiment, or an oil drop experiment, to determine the charge of the electron. That's what he ended up finding, was the charge of the electron. From his data, he was able to deduce that single charge by measuring the strength of an electric field that it was required to halt a free fall of an oil drop. Now, if we look at this atomizer over here, I want you to think about early 1900s. It was probably like a perfume bottle type idea, a perfume bottle that's spraying a fine mist of oil, right? That's what we have. Atomizers now that are a little bit more high tech than this, but at the end of the day, he had a whole bunch of dots up in this upper cavern. Now what happens is he had a tiny little slit in the middle of that positively charged plate so that the oil drops could go down one at a time. Now, he had some ionizing radiation, probably X-rays, that he was able to pinpoint right at that one electron. He had a light source so that he could just view it. Here he was standing over here, probably getting cancer from that ionizing radiation. Sad day, but still, that's life. And so the negatively charged plate, he understood that opposites repel, so negatively charged plate and negatively charged electron, they were able to repel each other at a specific charge of the negatively charged plate. And so what he wanted that one tiny little oil droplet to do was be suspended. He saw that the charge of the oil drop was always floating and whole number multiples of negative 1.6 times 10 to the negative 19 coulombs. And so that's what he determined was the single charge of an electron. Pretty awesome. From there, he was able to do stoichiometry to figure out the actual charge or the actual mass of the electron. So when we're looking at what he took from the charge to mass ratio was that he found the charge first and then was able to deduce the mass after that. So what we developed, we know that there are electrons. There are other protons. We were able to develop that too. That is not as well understood in terms of who developed it first. So we won't go into those experiments. But this is a very, very interesting fact right here. The plum pudding model is an early 1900s idea of what an atom looked like. Plum pudding, if you don't know, was a popular Christmas dish in England at the time, early 1900s. And what plum pudding was essentially our version of a fruit cake, if you've ever seen a fruit cake, where you take a whole bunch of different components, you just mix them all up together and you bake it and you hope for the best. So the early structure of the atom was this idea that protons and electrons were all just kind of swarming together, no big deal in this plum pudding model. We now know that is not true. What came after this was the Rutherford Gold experiment. 1909, Ernest Rutherford, who was working under J.J. Thomson at Cambridge, had subscribed to the plum pudding model, and he was performing an experiment to confirm this. This is what's great about hypotheses. You might have one, and it turns out to be the exact opposite of what you think it is. The gold foil experiment that Rutherford used, why not gold foil? He put some gold foil right in the middle, very, very thin piece, and he was able to take lead around a source of alpha particles. So again, nuclear experiments. An alpha particle is a helium nucleus. Just a helium nucleus right there. No electrons in that helium atom, just the nucleus itself. And those alpha particles being positively charged then, he was expecting a few to deflect, and he was expecting this idea of, oh, let's try to confirm the plum pudding model. And he did this experiment, and what he noted was that the experiment, most of the particles passed directly through. He was not expecting that. And what he looked at was the idea that, well, if there was an actual deflection, that maybe right in the middle there, you can kind of see it if I zoom in, a tiny little nucleus. And the protons and the neutrons must be encased in that tiny little nucleus. And so the positively charged species were a lot more dense than what he thought. It's amazing to think about the early 1900s, 100 years ago. All right, more nuclear theory. We developed the idea of the nucleus. Most of the atom's mass is in the nucleus. That's where protons and neutrons are. P with a little plus sign and N with a little N, a little zero is a proton and a neutron for me. Most of the volume is empty space. So electrons are dispersed throughout the majority of the volume, but the protons and the neutrons are encased in the center. We'll talk a lot about the electron cloud as we move into chapter 2. What we also get from this was that the Rutherford model was highly successful, but it did not count for the mass of the neutron yet. That wasn't until 1932. Look at that year, 1932. A student of Rutherford's, James Chadwick, demonstrated the unaccounted mass was for neutrons, neutrally charged particles. The neutron has a mass that is similar to that of the proton, but it has no electric charge. That is less than 100 years old. This chart is a beautiful chart to have just organized in our thoughts. Mass in kilograms is our standard SI unit, but we don't really work well with that in chemistry when we're talking about the theoretical. So we do have the idea of the atomic mass unit, the AMU. And so we have normalized the mass in kilograms to an AMU. 1 AMU for a proton, 1 AMU for a neutron, and effectively 0 for the electron. We do know their relative charge as well, +1 for the proton, 0 for the neutron, and -1 for the electron. So we'll be dealing with all of these as we progress forward. We're going to define some elements next class. We'll talk about isotopes, and we'll do some math with some calculations. Thank you all so much for joining me.